think we are good to go. So again, welcome everyone. So today's webinar topic is on, kickstarting your valve simulation journey, particularly valve flow simulation journey in just under 10 minutes with some easy 4-step things using Autonomous Valve CFD, shortly AVC. So to start, I'll introduce the speakers. With us today, with me joining Sandeep Jadhav, the man himself. He's our beloved CEO, and he has a master's in aerospace degree, like in engineering from IIT Bombay, and he has a wide experience in leading different product team, developing different product in CAD, CFD, 3D printing, so etc. So thank you for joining, Sandeep. And myself, Praveen, I'm the product manager at Simulation Hub, product marketing manager at Simulation Hub. And I have a rich experience of around 18 years in CFD, applied to different fields, like including valves, building HVAC, and stuff like that. And recently moved into product division. So with us, our young leader, Akshay Dorle. He's a business manager of AVC, the product which we are going to see. And he's handling customer relationship, customer engagement. He's responsible for all the product management, bringing new features and everything in say, like, yeah. So without further ado, I'll explain the agenda. So we'll start with a short live demonstration of the application. As promised in the topic, we'll show, how you can start your valve simulation in 10 minutes. Okay, Akshay will walk you through for a short demonstration of the application. And then we'll move to see some real life, application of those app business cases explained by Sandeep. Then I'll take over through different, what are the flow coefficients and Autonomous Valve CFD application, and the applications and success stories, more success stories we'll see, and we'll end with a Q&A session. So yes, I guess we're good to go. We have good number of people joined now, so it's good to go. Akshay, over to you.
Thank you, Praveen, for that wonderful introduction. Let's just straight away jump on the demonstration. I'll share my screen. I hope my screen is visible.
Yes, actually, yes.
Yes. So Simulation Hub hosts various products, one of them which is Autonomous Valve CFD. It's a web-based application. I'll just quickly log in. So along with Autonomous Valve CFD, we have products called Autonomous HVAC CFD and recently launched Buildings AI. I'll just quickly jump to the dashboard of Autonomous Valve CFD. So this is where you can actually visualize all your previous projects. I'll just quickly start with creating a new project. We'll start today with ADN 400 full offset butterfly valve. Just give it a quick description, and just with a couple of clicks, okay, we have just created our simulation. So as Praveen has mentioned, to start the simulation, we'll have to jump through 4 steps. First steps is inputting the CAD model. So I'll just quickly upload the CAD model. So butterfly valve. So this geometry is getting uploaded in the cloud. So we'll just quickly go through the CAD preparation steps as the geometry is getting uploaded. So for the simulation, we just need the valve with the pipes connected. We don't need to close the ends of the pipes. We need to have a specific upstream pipe length, which is 2.5 times the DN. It can be higher than that, but not lower. Similarly, the downstream pipe, it should have a length of 10 times DN. It can be more than that, not less than that. This is just how the schedules are formulated. And this is the opening position. Since we have two configurations, the details are given here, how we should upload the CAD depending on the configuration. And the bodies should be separate parts. So please do not combine the entire thing into a single body and upload. And we support CAD neutral formats like STEP, Parasolid, and the other formats like IPT, SAT. So I believe the geometry is uploaded. I'll just quickly specify the valve. So it's a flow regulation, rotation type. Say triple offset butterfly valve. And 400, we'll keep everything as default for now. We can specify the material, the pipe roughness. I'll just click on apply. It will apply the settings. The second stage is setting up the motion. So since it's a moving, it's a rotating type of valve, I'll just quickly select the rotating parts. I think this is the disc, so I'll select the disc. The shaft, again, it's very intuitive, just a couple of clicks, and you're good to go. So I'll just select the cylinder for the axis of rotation, and it will automatically populate the openings as such. So starting from 20-degree opening to 90-degree opening, you can also preview the openings. Let's say there is a stopper in your design, you can even reverse the design, reverse the direction of rotation. You can preview it. Let's move on to the next stage of the setup, which is the defining the flow direction. So just click on define valve connections. So here we are just setting up the direction of the flow. So we'll just have to select the inlet pipe again with just a click, outlet pipe, just a click, apply connections. It's very straightforward, very intuitive. We'll go to the next stage, and this is the run simulation stage. So I'll just click on run simulation stage, and that's it. So till here, it's pretty easy, straightforward. We'll go with standard resolution. So we have 8 openings, which will consume 8 credits. I'll just click on run simulation. So you can see here the message is submitting simulation job. And as with almost all applications, it's always good to give it a quick refresh. Give it a quick refresh. Fingers crossed. Yeah, so the simulation has started. There are 4 steps in the CFD process. So these are the steps. So right now it's in progress. And over to you,
Praveen. Thanks, Akshay. That was well under 10 minutes as we were promising. So the idea is we'll keep a watch on the progress of these simulations as we go through the webinar slides, and Akshay will keep you updated. Again, we'll go back to Akshay on result visualization part. Yes, Sandeep, over to you. Like you can. Thanks.
Thank you, guys. Nice presentation, Akshay and Praveen. Okay, so hi everyone. I'm the person who started this journey long time back. We have been working in a space of CFD now last 20-25 years. Especially simulation of CFD platform was started in 2015. We are completing 10 years of computing. And we have built 3 products. There is Autonomous Valve CFD, Autonomous HVAC CFD, and the latest one being Autonomous Building Simulations, which is also being now called as a Buildings AI. So whenever I talk to customer and user, that's one of the most favorite thing is trying to understand what's their business and how we help them. And they also want to understand why they should invest in a product like Autonomous Valve CFD. And so I thought I will talk about that till Akshay bakes the simulation and brings out the wonderful results. So Autonomous Valve CFD has been now used by a wide range of customers, starting from valve manufacturers in US, Europe, and in Asia. We have a valve manufacturing customer who are in control valves. We have a valve manufacturer who are in automated valves, or we have our packaged valves things. And then we also have a lot of customer who are doing on-off valves and safety valves. So Autonomous Valve CFD supports a wide range of valves types and the businesses. And uh, this is a really great journey that we are doing with our customers who has really large number of valve design. So if you know, every valve manufacturer has a API design, he has a ISO design. Again, there are design changes for the corrosive environment, type of fluid. So uh, it's a huge number of designs that they have, and for them, getting a right product in the hand is very, very important. So if you are selling a valve, one of the topmost priority for you is the that your valve has to operate. It's a final control of the system, right? And one has to be really careful about the liabilities and things that can arise because of the environment that it operates, right? So the valve performance really dictates, whether it will operate in that particular condition. When the valve need to be operated, need to be open or closed, it should be. And there are two things that are really important. One is a CV value, right? That the amount of flow that you are promising, it should get delivered, right, at that particular angle of openings. And the second thing is hydrodynamic torque, which is again a very, very important in torque calculation. Hydrodynamic torque plays very important role, and it's very difficult to compute using experimental result. Again, a simulation comes in a very, very handy at this stage. So these are the customer. They have been developing a different products, different product lines, and they have been verifying their design and supplying it in be it in oil and gas, be it in HVAC systems, water systems, chemical processing, underwater. So a very huge amount of application area. A lot of our customers design and supply their walls, and we are very proud to partner with them. So I thought I will present one business case that we are really proud of. That is with a Bray. So many of you will be already aware about a Bray international company. It's one of the largest valve manufacturer in North America. They have more than 40 offices across the globe, and really a great company which has a design center across the globe, designing a different type of products. Uh, in Bray, they need to test their valves. They need to verify their valves, and they have been doing it with a Utah laboratory, where if you send a valve, it costs you money. Average valve cost will be like $5,000. There's a lot of things. You have to first manufacture a valve, you have to package it, then ship it. You need to take an appointment. Then it gets tested, and then you get the result back. And experimental testing is the ultimate truth. There is no doubt on that. There is a if it when it comes to the gold standard of testing, it's experimental testing. But it is very difficult when you are having a really large number of well design, and when you want to do it for a number of new designs. So XCFD comes into a play where CFD also can be helpful, right? So and as any valve manufacturer, these are the choices that if you have a choice of using experimental thing, you can use a CFD, or sometimes you can also try to use Excel based calculation. A lot of that also is option. And Bray has been really focused on doing a laboratory testing. They already have their own internal setups, and they have been also using very generic CFD application to do that. So generic CFD application takes a lot of time. Even if you do in-house, it takes a lot of time. If you outsource or you find a CFD service company, they also charge you good amount of time and money. So they wanted to have a solution, and we reached to them and we presented our solution. They really validated it across the things. and they started to see the value that our product offers to bring up the accurate result to their designs. And then they could iterate over it very quickly, because our runtime is very fast. You can very quickly come up with a better and better design. So they become our enterprise customer from 2019. Um, they have been renewing our subscription from last 6 years, and they also use now. Earlier there were few users who were using it, now to very large number of users. Because the good part is that here you don't need to be really CFD expert to run this application. The part of doing computational modeling is done by our software, finding out the right boundary condition, finding out the right initial conditions, doing a proper meshing. All that thing is sorted as per your requirement. And then there is a huge amount of CFD they have been using it. If generally, if you see with any well manufacturer, you will do a few CFD, because the time is the constraint, cost is the constraint, expertise is a constraint. That all these constraints are removed by AVC. You just need to be a good valve designer. You just submit a design. At a one time, you can submit a 10 design also, and within a couple of hours, you will get the results for all of that. That help Bray to definitely save in a lot of cost in experimental thing that typically goes in. They're definitely still doing, and we also recommend all valve manufacturer to continue doing experimental validation. But it also now gets you in a the good product that is there, which you go in experimental. You don't get a surprise in experimental, right? So because you're already tested it, you already fine tune it, and then you get the final thing validated. It also saves sustainability. There's a lot of water and CO2 that get utilized in manufacturing, designing, iterating over a valves in an experimental way. So this is a way of conserving our resources and also optimizing the final design. And so this is the partnership that has gone along last past 6 years. We are really proud of working with Bray. We have learned a lot with Bray. We have grown with Bray, and it's we are meeting them, and they also always suggest us a new things to make the product meet what customers or the industry expectations are, industry standards are. And Brindesh has been a really great support. He has always gave us a really good input of how things need to be simulated design, and that has helped AVC and Simulation Hub platform to grow. As I said, to just conclude with this side, that there are a lot of benefits that a product like AVC offers. We have now developed a new business plan with them, like a unlimited credit access for enterprise customers. So you also can be get into that. So there is no tension about how much of credit that I'm consuming, so that you can just focus on designing a right product and bringing them fast to the market. It just helps you to get your go to market right. We have also validated our product lot with a Uta laboratory, our laboratory, experimental laboratory in Kerala. So we keep on always validating our product, improving our product. We are able to provide a consistent accuracy in most of the cases, 90% plus. It has reached to 98% also with experimental, but 90% is most of the time we able to deliver. Especially with a Bray, you will see that it helped them to bring up the new products, because the nice thing about our application is that it works from anywhere. So you access it from your laptop, you can access it from your desktop, uh, and you can really play with the really new novel designs. So if you see that this kind of design where there is a lot of a new part that is coming in, so even doing that CFD takes a lot more time. It is not more a project of 5 days. Sometimes this kind of projects can go to 10 days, 12 days, but we are able to resolve very fine passages and able to show you the benefit of this kind of new novel design in this. And then that helps our customers to win new contracts, large contracts, to get the things right. And so this also collaboration has gone in, like developing a new features for, like, say, how do I add a roughness to a particular part, because there are very small things that makes a big difference in a valve design. So that kind of thing we able to work. Bray has been really pushing us in a very good way, that they have been designing very complex flow passages with additive manufacturing. And then that means we also had to adapt our software to simulate those, still keeping it autonomous nature. So that is the part that we have able to deliver. And so if any one of you are wall manufacturer want to try this product, we welcome you. And there is a lot more value that I not covered into this, that I would like to share with each of you. So I think with this, I will hand over back to our team. Thank you. Would you like to share your screen? I can stop.
Yes, thanks, Sandeep, for the running through the business case, and that case study was really interesting. So, like, now the stage has been set. I hope you are able to see my screen, right? Like the slide. Yes. Okay, perfect. So we'll start with the fundamentals, touch base on the fundamentals, and then move into what are the methods to calculate and things like that. So it's a bit slightly late, but still, so valves is a device that controls the parameters like temperature or flow or pressure, depending on the loop they are installed in and the purpose, by adjusting the flow area. And there are the valve manufacturers has to evaluate and publish the CV or valve flow coefficient data for the complete range of valve sizes and the complete range of openings in the product catalog. So it will be useful. It is mandatory. It is useful for comparing different valves and selecting the right size for the application. So let's talk about that. But before that, definition of valve flow coefficient, CV. It is the volume of water that will flow through the valve with a given pressure drop for a unit pressure drop. So it's simply put, it's a flow capacity. So how much flow it can deliver upon a given pressure drop. So that's the definition. So it is calculated for every opening angle of the valve, and it's calculated using the formula. This is gives the flow rate, specific gravity of the fluid in which it's tested, and then the delta P, the pressure drop across the valve. So the importance is, as I said, it is used to compare different valves and their flow capacities and select the right size for the job. And it also it gives the information about the flow characteristics, how the flow varies as the valve opens. So some, depending on the profile of the trim and the valve design, some valve could be quick opening, which is required in for in nuclear applications to cool down. So you need immediate cooling down. So quick opening is required. In some cases, linear opening or equal percentages may be required. So depending on that, like CV importance is based on the flow characteristics, and you can size the and flow capacity. You can size the choose the right size for the job. And similarly, another flow performance character like coefficient is the CDT, hydrodynamic torque. It is specifically for the rotary valves. So it is the closing torque or torsional force created because when the flow passes through the disc, when it is partially open, there is unbalanced force created, pressure forces created on the front side and the back side of the disc. So this will cause a closing torque. So this is required to size the actuator rightly. So it is calculated for, similarly, it's calculated for the complete opening from fully closed to fully open. And then it's calculated, it is represented as a non-dimensional coefficient, CDT. So it's calculated by putting the dynamic torque and delta P across the valve and the diameter of the valve. And how they are calculated is in flow loop tests. First, we'll see this method. And there are different certified labs like Utah Water Research Laboratories in Utah, US, and the FCRA in Kerala, India. So these laboratories follow the standards like ISA, ANSI ISA 75.02.01 standards, where the setup to conduct this flow loop tests are specified. So it's specified, for example, what should be the pipeline mentioned, where you should measure the pressure, keep the pressure tappings. For example, 2D at the upstream side and then 60 at the downstream side to measure the pressure. So delta P will be measured across this. So similarly, there are other standards which talks about how to calculate CDT like M49 manual. And there is a slightly different procedure, like, they use strain gauges attached on the valve shaft to measure the shaft torque. Okay, and then use it. But the test setup mostly mimics the previous one, like 2D and 6D pressure tappings and such. So how these flow loop tests comes in the whole workflow of new product development? What happens in the new product development? Let's say the company decides to launch a new product. It comes up with a design requirement. In short, like target flow capacity and stuff. So that goes to design engineer, and the design engineer designs the valve, and it goes to the manufacturing, the prototype of the design, first design. And then the prototype is shipped to the flow loop test facility located in some remote location. And then the flow loop test, like the facility lab facility conducts the test and provides you with the flow, what is called flow performance report. It has the CV and CDT for the complete range of opening. So that is provided. So you get the CV data and CDT data. And now you compare the target CV and the achieved CV. And if it is not met, then the design engineer makes some corrections or improvement, and then the process follows. So approximately one cycle, I'm considering only the testing duration. So that takes weeks of time. And depending on the workload in the lab, you have to be in queue, and it gets, wait for your valve to be tested, and then the reports are submitted. So there are, you can imagine, if there are multiple design iterations involved in improving the design, so you can you can imagine the cost and time involved, right? So what are the challenges of this flow loop test? It provides you with limited flow insights. So the report, what you get from the flow loop, has the end data, that is the flow capacity, but it doesn't give you any idea about what went wrong or why it is low, where the cavitation is prone, like where cavitation prone zones, what I need to improve. Design engineer, based on his experience and the final CV data, he does some corrections in the hope that it goes in the right way. But it doesn't provide a detailed, flow visualization insights. So that is one challenge here. And the other challenge we already discussed, the cost and time factor involved in every design change. Okay, you need to do the changes and prototype, manufacture the prototype and ship it. And so the third one is the resource limitation itself. For large size valves, there is a limitation in the lab facility itself. Okay, so there it falls short. There this may not work. So what are the other alternate methods to flow loop test? One is analytical and the other one is numerical. Analytical, the accuracy is low, but the time, cost, and skills required is, comparatively benefit. On the other hand, numerical methods, the accuracy is very close to a flow loop test. But compared to the analytical, there are some challenges in time. So we'll see, the challenges in each method. Challenges of analytical method is, you already know it's empirical relations, and it doesn't account for very minute details of your design. Your trim design is changed, so how it will reflect in the formulas. So that is a challenge. So then comes the CFD or numerical method. So CFD is nothing but you're solving the Navier-Stokes equation, mass, momentum, and energy equations in the fluid cells. Like fluid domain is discretized into what we call as cells. So yeah, it's a separate science, and I don't want to burden you with too many details of CFD. So now moving on, what are the benefits of CFD? So the benefits of CFD is it provides the visual data. So for example, the velocity, pressure, everything can be mapped in each and every data point in the whole flow domain, flow path of the valve. So this gives you the complete understanding where there are flow separations, where the pressure is very low, and where it is prone to cavitation. So those kind of details you can get. So the conventional CFD approach has these processes. So first you need to extract the fluid volume and do some cat cleanup on it so that you'll be able to generate what is called mesh. And then you need to select the right and appropriate turbulence models, numerical schemes for this underlying physics. So once all these are set, then the in-house, high performance computation machines are required to run this heavy simulations. And after the simulations, you get the colorful, the results visualization and the qualitative as well as the quantitative data. So now imagine you need to repeat all these things for every opening, and then you will arrive at the complete curve. So all these it needs expertise, and depending on it's like CFD is kind of art. It depends on the artist. Actually, it should be science. The artist, I mean, the user who is dealing with the CFD, who is creating the mesh or setting up the numerical schemes, depending on him and his level of expertise and experience, the results will come. So we want to make it a science. It doesn't matter whether you have experience in CFD or not. Like, your intent is to predict the performance or flow capacity of your design, right? So it should be with the designer. Make it science. It should work. It should give same results for any users. That's the thing. So in this vision of democratizing the technology, we already talked about the challenges. So it needs expertise, it needs high power computing, and software cost involved, and annual maintenance costs and whatnot.
So Praveen,
So
I would like to add a few more bits on this.
yes,
Is
yes,
that
yes.
so I think Praveen has really touched the nerve of why you need to move from conventional to autonomous CFD, especially for the valve domain. So what the process that he said is for a 8 angle of opening. So you can think, oh, okay, 8 CFD simulation that I have to do. The next thing is that if you follow the ANSI standard procedure, for every angle of opening, you need to run a 3 CFD simulations. First is to do a first initial guess estimate to reach that 1 bar of pressure drop, right? Then you need to do second CFD simulation and then third simulation. So it's actually 24 CFD simulation that you are performing, right? So 24 CFD simulation, you can say, okay, no worries, I have a computer and I will do it. If you have a simple straightforward valve, butterfly valve or something, no worries, that you can still do it. But think of that you have a ball valve where your pipe friction itself could be a really dominating pressure drag, right? So coming with that, your mesh counts increases just by 10 to 20 factor. So you are working with a really large mesh. You are working with if you want to reach to the experimental result, you always reach to something like 20 million mesh, 30 million mesh, 40 million mesh. And then you want to add perforated, let's say, pressure drop devices. Again, your mesh count increases. And that could be done for 24 simulations. And that means if you go to next slide, Praveet, is we have seen many of the CFD users do not have this detailed level of understanding. How do you do that? If you go to a valve size, like a smaller valve size, 2 inch, half inch, again, the whole thing changes. It is not same boundary conditions, same thing, what you do for a 6-inch wall, 8-inch wall. If you go in a higher sizes, 36-inch, 48-inch, again, the things changes. You need to come up with a different scheme, different turbulence model, and different part of it. Hardware computing, as I said, is a really huge thing. Some of these things can go run more longer time. And then the most one is the software licensing cost. So if you see generally many of our the generic CFD software, I will not take a name here, each of them comes with a one thing, is like there is a one big cost of one license. Many of the time it's a single core license, right? It works with a single core. It works for a single user. Now, if you want to run this for 24 simulation with a 30 million mesh count, or for this, you need a HPC licensing. So HPC licensing comes with a 12 node. So if you want to run it, let's say you got nowadays on AWS, you can get a 96 core computing machine. So you need so many, again, HPC licensing. So the total amount of HPC licensing again becomes really, really high. And after that, your actually role is to design a better valve. CFD or the flow performance is just one aspect. You are also bothered about FEA. You are also bothered about material cost reduction. There are so many other things that you are supposed to be doing than just do this. So what we feel is that there's a good tool which gives you really cost-effective solution, highly validated, highly accurate, and that it makes sense to move to this. I will not say that you shouldn't use other generic software. Like if you want to do really complex flow phenomena, you are doing like a two-phase flows, you are doing steam and water flows, use these things. It's like you have you want to dig a hole at your backyard. You don't bring a JCB. You need a small tool, a right tool to do that. And Autonomous Valve CFD is that tool to do that job right, very quick, very fast, accurately. And that's the I think thing that has really helped. And it is following the proper flow loop testing procedure. It is over the years has fine-tuned each and each of this parameter. And this product is meant only and only for the valve simulations. Generic simulations are meant for doing a simulation, flow past an aircraft or flow past an some X and Y. So there you really need an expert user to do that. And even expert users, if they do it again and again, there is no repeatability. In AVC, you give a design, every time it will produce the same output for the same design and any user. So there is that kind of value. So if you change a certain parameter, let's say you change a surface roughness parameter, you will get a different outcome. So these are the design parameters is what you play with, and that what matters a lot. So I just wanted to bring that difference
Yes,
because
yes.
many of the times uh, it looks like it's automated CFD. It's not automated, it's autonomous. And the big part is intelligence. Actually, if you see how to create this computational model is the real 90% of the real game in this business. So I just wanted to highlight that. Right, please continue.
Right. Thanks for bringing up that point. Yeah. So as Sandeep mentioned, with that vision of bringing this technology to the hands of designers, and we developed this autonomous valve CFD. It mimics the same flow loop test on a computational or virtual mode. So that's why we say it's a virtual flow loop testing application. So it follows all the standards, provides you with all the flow performance parameters like CV or KV, CDT, and we recently added incipient cavitation index as well. So it is powered by Autodesk Platform Services for visualizing the model, handling the geometry CAD part, and visualizing the flow on the web platform. And then AWS Amazon Web Services for running the computational fluid dynamic simulations. And OpenFOAM is the solver which you use in the backend. And it is all powered by simulation of platform services API. So we'll show that. So to simply put, what it takes as an input is the valve CAD model itself, the flow direction as Akshay showed, and the opening conditions for which you want to simulate. Once it is done, then it provides you with a set of outputs. So I divide that into two major categories. One is the qualitative inputs, like the velocity contours, flow lines, pressure contours. That will give you the flow visualization, the insights, where the flow pressure is low or flow separation happens and everything. The other one is quantitative data, which is the flow performance data itself, the CVCDT, head loss coefficient, cavitation index, and everything. So all these things combined, the third output is comprehended in one single report, which is auto-generated, and you can ready to, it's in a form where it is ready to handle to the end client. So that's how it is. And it supports all the type of valves in both control as well as isolation categories, both rotary and linear motions as well. Now it's time to have a quick check on Akshay. Akshay, what is the status? And after looking at the status, he'll also walk you through the result stage. That is the second part of the demonstration. Yes, over to you, Akshay.
Yes, thank you, Praveen. I'll quickly share my screen. So as you can see, the simulation is going good. Solve is running for 7 conditions, and we have moved into the post stage for one of them. So in a few minutes time, it should be completed. For the easiness of the demonstration, we have run it earlier, and we'll just go through the stage, how it looks, what are the visualization parameters and methods we have in the application. So as you might have seen, in the solve stage, a couple of conditions were in green. So once it's completed, it will be in complete blue. And yeah, just go in the result stage now. So result stage, it has these 5 options. So we'll start with the performance data, which is like the most needed by any valve manufacturer. So this is like a consolidated report. Here you can see the flow rate, the pressure drop, gross and net values, flow coefficient, CVKV, the head loss coefficient, and the hydrodynamic torque coefficient. You can also export this in terms of CSV. You can also visualize the parameters in individual graphs like such. So this is for the gross CV curve. You can see how the characteristics of this particular design is. We also have KV. Again, we can export it. We can save it as an image. We can export it as a CSV. Similarly, hydrodynamic torque coefficient. Similarly, head loss coefficient. So the crux of doing a CFD simulation is to be able to visualize it in 3D. So one of the parameters is flow animation. We'll just quickly go through it. So this is how you can visualize it in the viewer. You can see where the flow is accelerating, where it is recirculating, how the flow lines are. You can also just rotate the geometry. You can even click good pictures and have it in your catalogs. And you can also play around with the angle of openings. So I'll just, for now, just go with 50%. And just a couple of seconds, and this is it.
Might be you can hide the pipes. I think that will help to see.
Sure. So yes, this is how
it's like any 3D CAD software that you have been using, whether it be Inventor, SolidWorks, Creo.
yes.
It has all the functionality. It has a functionality to section the model. It has a capability to measure the things. So and it can really definitely, as Akshay mentioned, you can always create a great animations and videos out of this to demonstrate to your customer how your valve is right design.
Yeah. Even you can adjust the speed for the flow lines. Moving on to the next one, it's the contour plots. So here, what we can see is how the flow is basically accelerating. Maybe there is some stalling here. Maybe it's separating here. It's recirculating. So
I think if you see, if you a little bit zoom in, you can see there is a very small step sizes, which makes a very big difference in the design. So the point what Praveen was mentioning, that there are definitely people say, I have a formula. I have analytical things. This analytical thing cannot capture this. And we have observed even a step size of 2 millimeter, 3 millimeter makes a huge difference in the torque, that the pressure drop that you get. And CFD is the right tool to do that, and AVC is able to capture effect of each and those parameter, and it helps you to design efficient valves. Yeah.
Yes. So speaking of pressure drop, we can also visualize the pressure here. So this was velocity. We can also visualize the pressure. This will give you, where there's a high pressure zone, where it's a low pressure zone. So here you can see it's
a beautiful picture.
Yeah. So at the tip here, it's creating some sort of a low pressure zone. So,
And even you can move those slides at
Yes.
every part of it. So it doesn't limit you because it's a web application. You can go to any step or any stage within the model. I would say it is even faster than many of the desktop applications because you don't need to create those posts yourself. That those are already pre-baked for you. It just based on your internet speed loads it very quickly within your applications. Yeah.
Again, at every visualization, you can play around with the angle of openings. For, let's say, 30-degree, it might have a small flow area at the top. Again, it can give you very good insights to what's happening with the physics of the flow.
I think we can
This
move
is-
to a report, Akshay. We have just now
Sure.
minutes. I would like to have some question answers. So
Sure. So at the end of the simulation, this is the consolidated report, which is autonomously generated. It has everything that we just saw. So it will have your, executive summary, which is the tabular data. We have the graphs of all the tabular data. We give a brief background of the process. We give a brief background of the CFD methodology. We show the formulas that we have been using for the various calculations, and also visualization. So this is for all the 8 openings, velocity contours, all the 8 openings, pressure contours.
and you can use your branding. You can use your own logo,
Yes,
your
yes.
format. So the report itself can be customized with there is a configurator where you can
Yes.
just change the report to meet your part. You want to include your customer names and things, units. So there is a plethora of things that is available there.
If you have a customized report option here, you can just use it to do the things that Sandeep sir just said. Yeah, so that's about it. Over to you, Praveen.
Yes, thanks, Akshay. I'll just take a few minutes before we take the question. And so hope you're able to see my screen and coming back to where we left. So I'll show you one interesting case where we showcase, how we can reduce the time to market. This was a special case where before the product development stage, we ourselves were using conventional software to provide consultancy services for different companies. So one such case was have a globe control valve with cavitation cages. So that time it took us, it was back in 2012 or something. So that time it took us, 7 to 10 days, like 1 week to 10 days to completely come up with CV for all the openings. And now we are able to do it in 1 hour with the help of AVC. So that's how quick it is. So we reduce the days simulation results from days to hours. So that will help you in supporting on-time delivery, accelerating the design optimization process and stuff. So how it is done, it's all happening in the cloud. So it assigns 36 core dedicated EC2 instance, and depending on the mesh count and the size and complexity of the geometry, you can increase the core as well. So to accelerate the simulation results. So then simulation of APIs comes into picture. It does all the cat cleanup, meshing, and solve, and provides you with the results. So this is again explained. Everything runs in parallel. Multiple designs can be run. Multiple angle of opening can run parallelly and stuff. So how accurate is your results? We understand everything looks like a magic, right? Like, you just click next, and then the CV curve is there. So we understand with great responsibilities, like, with great power comes great responsibilities. We need to be sure about the validation. So we have done a lot of validation studies with different types of valves and compared with the lab data results from FCRI and Utah Water Research Laboratories. It covers butterfly, ball valve, segmented, full port, everything, including globe valves, and covers a variety of a range of diameters, range of valve sizes, different flow capacities. So what we have observed is we fall in the range of plus or minus 5% deviation. So above 90% accurate results are there. So some more customer stories, but considering the time, I guess I'll quickly rush to the end. So there are different, maybe we'll email you with the
We
slides
need
and
to have
things.
a
Yeah.
one more webinar for this.
One more webinar too. So recently we added a new feature to capture anti-cavitation trim design. So with the help of which we can now simulate very complex geometries made from additive manufacturing or 3D printed geometries as well. So we are also working on, this is the upcoming feature we are working on, liquid recovery factor. So cavitation index is already done. Now we've moved into liquid FL. So this is under progress. We have already presented a paper in last Valve World Düsseldorf, and we are accelerating things to make it in production. So what next? You can straight away start with your trial subscription plan and try experience your own Valve models, or schedule a call with our expert with Akshay and me. We'll guide you through to address your challenges or requirements specifically. So with that, we come to the end of this webinar, and we'll do a Q&A session. We have got some quite good amount of questions. So the first question is from Saroj. His question is, you didn't provide any input like boundary condition, how it's calculating automatically. And are you like, that's the main question. So Akshay, would you like to take that?
Sure, Praveen. So that's the power of the autonomous workflow we have developed. So the design engineer doesn't need to worry about the boundary conditions and the other parameters like the meshing and boundary layers and all of this. This is all taken care by the autonomous workflow. Just need a CAD model and that's it.
Yeah. So what it does in the backend is it does calculate the CV based on the 1 bar pressure drop category. So it does apply all the inlet pressure boundary and outlet pressure boundary. It sets up the what do you call, the turbulence models. It monitors the residuals, everything it happens, but it's in the backend. So yeah, that's taken care.
So that is basically to meet the ANSI standard for the flow loop testing. That's what we do that, and it's not the one boundary condition for all. That's the difficult or interesting part of it. That as per the valve, as per the mesh that you have done, so you go on doing it to meet that 1 bar pressure drop. So that's when then you meet that ANSI requirement of flow loop testing definition, and that makes it more accurate and able to meet experimental close band results.
Right. So another question is about the data security part. So how secured is the data on the cloud? Yes. So Sandeep, would you like to pitch in?
Yeah. So this is hosted on AWS, where all of you are doing any of the application today. If you are doing a make my trip, flight booking or anything, everything is now hosted on AWS apps, where your bank, credit card, every information is there. So ours is also put on highly secured environment. We have done a various certification from AWS to make sure that the data is encrypted, secured, and maintained here. Even if you want us to help in, suppose there is some failure in a simulation, you have to grant permission to our design engineer to access your data, and then only he can open and look at the design and model that we have done. We also have a two-layer authentication process available. So you can use email plus OTP. There is a one more option of geofencing. So in that you can say, okay, from this area of login only allowed. So if you have a design center, let's say in Houston or in Bangalore or something, you can geofence, and then only that also is a part. And then the one more secured aspect is that you also can restrict it only for the email address from a particular domain. So if you are, let's say, from Bray, or if you are from Emerson, if you are from any company, and then if you have bought that enterprise subscription, then only that organizational access is there. Even we can restrict the IP addresses. So that's another part of it. So it's a highly secured infrastructure that we have built, and uh, even our partner in this is Autodesk AWS services. They are again highly secured. Those things.
Okay. So there is another question from Suraj about cavitation. Can we also find out cavitation? Suraj, it's a tricky thing. One is, we do find out incipient cavitation index. Okay. And we are working on cavitation with the objective of finding out FL. That is what in progress that will be released in next quarter or so. We'll definitely connect. But multi-phase, full-fledged advanced multi-phase flow simulation is not supported as of now. But we can connect, and our team has the capability to handle this. So depending on your requirement, we can package it that way, and then we can see how we can address your requirement.
Yeah, I think the incipient cavitation is really valuable because that is the point beyond which you don't want to operate your valve. So that is by default, I think for every simulations we are computing you and giving it. And I think that's your safety limit. So that is the part that we are giving it, that, okay, you are reaching there or not. And so that's a really good value. And a lot of our customer are using that data to make their design decisions. So that way it is available, but there are some customer who wants to know in the cavitation where the bubble is forming, where that bubble is hitting, and that sort of thing. That sort of part we are not added yet because it would add a cost and computing, which is not required for the many of these flow loop standard testing aspect.
Yes. So the next question is about the mesh type and what happens in the backend, that kind of stuff. So I think I just managed to quickly pull out one slide on that. So what happens is the cat cleanup and even the mesh. So we generate hex dominant mesh with prism layers to capture the boundary layer. So all these things are taken care, and this is it. The algorithm identifies the shape and the flow area, everything. It automatically refines the mesh as well. So upstream, and as you go near the gradient of the shape or near the edge of the disk, so the refinement level increases, you can see here. Then the number of prism layer is also adjusted to satisfy the Y plus, to capture the boundary layer profile exactly. And
so
this
autonomous aspect, if we just go back to the mesh thing, so the autonomous aspect or the intelligent aspect is that it looks at the valve design, type of design. So it knows for a butterfly valve where I need to resolve my flow region. If I am a ball valve, where I need to resolve my region. If it's a segmented ball valve, where it need to resolve. If there are cages, where it need to resolve. How many layers that need to be added. And if you do that, if anyone who has actually burned their hand with a mesh know that mesh goes wrong. So it also has a way to read the report of mesh failure. So it's not that in our case it doesn't happen. It reads the mesh reports, then takes the corrective action, runs the second level of mesh, then it checks again whether it meets our quality criteria. If it not, it keeps on going on, I think 5 times till if it finds that no, it's really bad geometry or something, it goes on doing that and brings that part, and that is done for all, I would say, 24 simulations that might be there, because with the flow also our mesh type changes. So there are things which is really detailed way that we adjust and accommodate the mesh requirement to meet the physics requirement in this case.
Yes, it does all the residual convergence, pressure monitoring, and CV monitoring, everything in the backend. So the algorithm takes care of all those stuff, whatever you do in a regular CFD process, but in an autonomous mode.
And if the convergence doesn't happen, it goes back and change those parameters and again runs it. So there is a total ownership of running a simulation is taken care by our software. It's not that it will just say, oh, it's not working. It will go back, it will go and try. And if it really not able to do, then only it will come to you. So yeah.
Perfect. Well said. Yes, Akshay, then is another question. What happened to the simulation? What's the progress? Somebody is curious.
Okay, Praveen. I like the excitement there. Just monitor it quickly once. So we are into the post stage now.
So solve is completed. Can you share your screen just?
Just a second. It's loading for me. Okay.
This is great. At the start of the webinar, we started the simulation, and the setup took us less than 10 minutes.
So
and now
post for 2 is
this
completed. Solve is
very good.
also almost completed. Yeah. So
very nice, very nice.
So I think the key part is that you just need to spend some 5 to 10 minutes in setting up the thing, and then as Akshay said, you can do it for really a number of valves, and then just relax. You are going to get an email that this is done, and it is taken care of: meshing, solve, post processing, report generation,
Yes.
visualization, every part of it. So I think that is a very, very high value thing for each of the end user.
Okay. So we just come to the end of this webinar. I guess there are questions, but I guess we'll take it. We'll answer them through email and connect. Thanks everyone. Thanks panelists like Sandeep and Akshay, and thanks the attendees for joining and making it more interactive. So thanks for joining. So we'll connect soon with the next series of webinar. Yeah.
Thank you for joining our webinar, giving your precious time. We would love to talk to you. Please try out our platform and give us the feedback. Thank you.